In another video, we discussed AND gates and OR gates. In this video, we're going to be discussing NAND gates and NOR gates. Or another way of saying it, not and not OR. And the reason you can say it like that is that what these digital circuits really are is sort of like taking an AND gate and an OR gate and attaching a small NOT gate at the end of them. What this does is it basically takes the output of what an AND gate or an OR gate would have been and inverts them. So for example, for an AND gate, if the output, we know that the output would always only be true if both inputs are true. Hence, these both inputs. So if this were an AND gate, 1 and 1 would result in true. But since it's been inverted at the output, this would actually become false, and everything else that would have become false in an AND gate would now become true. And the same applies for an OR gate, for a NOR gate, sorry. So for any output, it would be the opposite of what an OR gate would have yielded. So we know that an OR gate is always true unless both outputs are false, in this case right here. And since this is a NOR gate, and that is getting inverted at the output, this would actually result in true, and everything else would be false. Like that. We can see this in the simulation here, where when we run the simulation, where the AND gate, normally 1 and 1 would have resulted in true at the output, but now it's resulting in false because it's getting inverted at the end. And we can see everything else resulting in true. Same applies for the NOR gate. 1 and 1 is resulting in 0, whereas 1 and 0 also resulting in 0. Same thing should happen on the other end, but 0 and 0 will result in 1 because it's inverting the output of the OR gate. Now, remember how I said that it's almost like adding a small NOT gate at the end? That's what this little circle is. Well, we can show that. If I were to stop the simulation and take out this NAND gate and add a regular AND gate, and instead of using a built NAND gate, I were to like artificially make it with just adding a NOT gate at the end, we should be able to mimic the same behavior of a NAND gate. There we go. And if we run this, we can see that 1 and 1 results in 0, and everything else results in 1, just as we would expect a NAND gate to behave. So these two components, an AND and a NOT, have created a NAND gate. Now, the reason these are really important is that NAND gates and NOR gates are considered the fundamental gates, or some of the fundamental gates, in that any other gate can be constructed from them. And in fact, in practice, it is often good practice to construct AND gates from NAND gates, as odd as that sounds. You would take a NAND gate and invert it again to result in an AND gate.